this mic on? Can you hear me in the back? Is the mic on? Yes or no? Yes, it's on. All right. It is, no, it's not on. I didn't think so. It's just that I can, or sometimes I can fill the room without a microphone. So let me just see. Is that, there we go. Yeah, all right. Oh, I can hear myself now. Okay, so I'm dropping in the lecture on coronavirus today into the middle of the class. We outlined the change in readings. Who here has seen Contagion? Okay, those of you who haven't seen it, you might want to see it. It's a very easy assignment. All right, and so are there any questions about the other material we've been discussing before I discuss coronavirus today? And we can have a very interactive session, so you're absolutely free to, pause and ask me stuff at any point. So, let's see here, hold on. Okay, so epidemics actually have been with human beings for millennia, and people have actually been able to appreciate this. Human beings have been aware of the spread of epidemic diseases in their midst, and many of the responses that human beings have had to epidemics have been pretty much the same since time immemorial. Distancing themselves from population centers, avoiding contact with other people, or avoiding what they imagine to be, of course in ancient times, the causes of epidemics, such as bad gases, for example, or other kinds of things that they thought might be spreading. So we have ancient accounts and more recent examples of epidemics, and they are not new in terms of how they affect our societies, how they kill us, and in terms of how we respond to them. And I understand that they're scary, and once in a while they're serious, but they're not always deathly serious. So coronaviruses, the subject of today's discussion, are enveloped, single-stranded RNA viruses, which encode the largest known RNA virus genomes in the class. And those genomes range from 26 to 32 kilobases. In humans, these infections are associated with upper and lower respiratory diseases, and they can range in severity from the common cold. One of the causes of a common cold is a very common coronavirus. Just get a cold is no big deal. To SARS, severe adult respiratory distress syndrome, which is a more serious condition, and in some cases can kill you. The particular virus that is the cause of the coronavirus pandemic that's raging on the planet today is known as SARS-CoV-2. These coronaviruses, like other coronaviruses, are enveloped in lipids. So as the virus reproduces within the cells of the human host, as it erupts from the cell, it takes with it a little part of this human cell membrane. So it's encased in this lipid. Now this is important because this encasement is what makes it easier for the virus to spread from human to human. So when the virus leaves my body and comes into your body, it's coated in a kind of thing that would make it seem familiar to you, like a human cell membrane. But it's that same feature which makes some of our interventions more possible, because you can use soap and water to kill the virus. Soap, you may remember, dissolves or can help break down fats, which is what a lipid envelope is. And so that gives us a tool to attack the virus. The S protein in the virus, which is one of the components of the virus, it is felt, and scientists are still working this out, probably enters other human host cells by binding to something known as the angiotensin, the ACE2 receptor in human, an angiotensin receptor in humans, and that's how it enters cells once it leaves my body and goes into your body. The current pandemic probably originated in bats, just like in the Contagion movie. It's not fully understood why so many serious respiratory diseases in humans and other diseases come from bats. One of the theories is that male bats, of course, are mammals, that their immune system is very similar to ours. And so viruses that are able to take root in bat populations adapt to the bat's immune system. And once they adapt to the bat's immune system, they're like perfectly adapted to our immune system. So if they're able to make the leap from the bat species to our species, they're already ready to infect us well. This doesn't always happen. There are other viruses and bacteria that affect other animals that just don't affect us. Just like you may have noticed that why don't dogs get the human common cold? They don't. You live with dogs, you get the cold, they don't get sick. And sometimes dogs get sick and they don't spread the disease to you. Pathogens are optimized to particular species, and yet when it comes to these types of coronaviruses, they often can lead from bats to humans. In the particular case of this pandemic, there's some evidence in the genome of the organism that it may also have spent some time or acquired some genes or some features because it infected pangolins. Pangolins are a little cute aardvark looking, a little plated animal that's often seen as a delicacy in China. They are going extinct from being eaten by humans, and but there may have been some role of pangolins as well, and that's not fully yet understood. Now, what is sort of, how rapidly has this infection taken root, and what are some terminology that we can use? It first appeared in late December in the Wuhan area of China. It was called the Wuhan virus initially. We're not supposed to call it that anymore. It doesn't matter where the virus came from. Viruses originate all over the world. By early January, it was called the novel coronavirus 2019, nCoV 2019. And more recently, it's been given an official name, very rapidly in the last few months. The virus is now called SARS-CoV-2, Severe Adult Respiratory Syndrome, Severe Adult Respiratory Distress Syndrome, which there are previous SARS viruses, but this is the new one, CoV-2, and the disease is called COVID-19. It causes, the disease that it causes can also be called Severe Acute Respiratory Syndrome Related Coronavirus, SARS-CoV. So there are all these names floating around. I just call it coronavirus or COVID-19. There are hundreds of different strains of coronaviruses, mostly that circulate in bats and in civets, but there are two key strains that are concerning to us here. One is the original SARS, responsible for the SARS outbreak in 2002 and 2004, that was pandemic, that is to say it spread out around the world. The pandemic means that it's in more than one region, but there weren't large numbers of people that were affected. Or SARS-CoV-2, which is responsible for the current COVID-19 epidemic. Now, what happens when you get this disease? Chinese scientists have been working at a phenomenal clip. In fact, scientists around the world have been working at a phenomenal clip. Hundreds of papers have been put online and have even been peer-reviewed and appeared in fantastic journals just in the last 2 months. This was one study that appeared in the New England Journal of Medicine a week or so ago. This involved 1,099 patients that had laboratory confirmed. A test was done to confirm the disease from 552 hospitals in 30 regions of China through the end of January. So that's like as of a month ago. That's an extraordinary pace to do the science and get it published. In this population of Chinese citizens, the median age was 47 years, and 42% were female. It seems to strike men more, but that is an artifact of its occurrence in China. Smoking rates are much, much higher in China in men than in women. So male lungs in China are much worse shaped than female lungs. So the excess prevalence in men in China is felt to be an artifact of cultural norms about smoking in China. I don't think that will persist in other parts of the world. Of these patients, 5% were admitted to an ICU. That's a percentage that we're seeing consistently around the world. It can be quite a serious disease. For example, in Italy, a similar percentage, actually a bit higher. 2.3% had to have invasive mechanical ventilation, and 1.4% of the afflicted individuals in this first group from China died. Among non-residents of Wuhan, 72.3% had contact with residents of Wuhan. So the disease starts there and begins spreading socially outward from that location. The median incubation period is about 4 days from when you get the disease to when you start manifesting it, but the range can be between 2 and 7 days. And if you're hospitalized, people typically spend about 12 days in the hospital. Now, very few of these people in this cohort had any history of direct contact with wildlife themselves. About 2% of this sample had actually themselves had contact with wildlife. And 3.5% of these people in this sample were healthcare workers. This is a persistent problem that we're seeing in reports around the world. So either people come to the hospital nowadays with a flu-like illness and they're taken care of by healthcare workers, who are unaware that the person might have this new virus, so no special protection is taken, then those healthcare workers become sick, and either they are so sick that they too are hospitalized, which takes them out of commission, which means as the virus proceeds in our population, we lose our first responders, or if they're not sick, they become aware that they've been exposed to someone, and then they have to quarantine for 2 weeks. So for example, so many healthcare workers were either exposed or sick in Italy, in the Lombardy region with the Italian outbreak, that they had to call doctors out of retirement to help provide the care for the people in that region. So this is a serious problem, and it's happening right now in our country. In Seattle, for example, many EMTs transported the initial cases from the nursing home before it was known. They're all under quarantine. Other healthcare workers are getting sick. In fact, there's so many connections in my own lab. In my own laboratory, we have one person who was friends with a doctor who died in Wuhan. We have another person whose sister is a doctor in quarantine in Italy. And my sister-in-law is a doctor in Seattle taking care of these people as well. So, you know, even in my little group of people, there's so many connections. This epidemic is so widespread and affecting so many people. Now, thankfully, we humans mount a broad and substantial immune response to this virus. We are able to fight it. It's not something so alien to us that our immune system is overwhelmed by it. For example, like the HIV virus was very devastating, specifically because it infected cells of our immune system. Now, one of the serious problems that we're having right now with the epidemic is that the prevalence of asymptomatic cases is unknown. That is to say, we don't know how often the virus infects people but gives them no symptoms. And this is a very important parameter, because without knowing that, it's very difficult to estimate how deadly is the virus. If the only people we see, let's say if you had 100 people that are infected, 50% have no symptoms, and then 50% come to the hospital, and one of those people dies, you might think, oh, there's a 2% fatality rate for the condition if you divide 1 by 50. But if you divide 1 by 100, the true number of people infected, there's a 1% fatality rate. So the lack of knowledge about how many people are asymptomatic is hampering our ability to really understand how serious this disease is. Another study published by Chinese scientists looked at 45,000 confirmed cases in China through February 11th, a more recent date. It found that mild disease was present in 81% of the people. Most people who get the condition, it's mild. Severe disease in 14%, and critical disease in 5%, of whom in this sample, 2.3% died. Now, the true case fatality rate, as I've already just mentioned, is very difficult to estimate, and it's still not clear, given a whole host of clinical and methodological complications. And one of these complications, as I mentioned, is this issue of testing, which is very much in the news in our country right now. Some of you may have heard or seen the Vice President's press conference from the other day. And the problem is this, that there are many policy determinants whenever there are epidemics that can supersede and interfere with optimal public health response. And we're seeing that play out in our country right now. In fact, in countries around the world in different ways. Narrowly with respect to the testing issue, we have the following kinds of problems. There's a political desire for calm. That we don't want to create panic, and I certainly don't want to create any panic. Even though I'm speaking to you in this very pressured, animated, excited way, it's not my intention to alarm you. I'm just excited about this topic intellectually, and from it's like public health nirvana for someone like me, you know, like something is spreading in networks and it's serious. I'm like, I can say something about that. So there's a political desire for calm, which is understandable, but the problem then is that it often leads to skewed announcements and briefings, and sometimes even outright factual errors or even lies on the part of very senior officials, including, sadly, our president. There was a serious goof with the CDC. This is extremely uncommon for our Centers for Disease Control, which is a world-leading organization. They released the test late for use in our society. There wasn't a lot of the test available, and there are 3 little segments of nucleotides that are used to test for the RNA, and one of the 3 so-called primers was wrong. And this resulted in false negative tests when the test was first rolled out. Initially, our CDC promulgated what was far too narrow a case definition That is to say, initially they required someone coming to the hospital with an unusual presentation for the flu. In order to test them, they had to have recently been to China. So people in our society that were presenting with a condition that probably was a coronavirus infection, which they had gotten from some other person, but they themselves had not been to China, were not tested. So we were flying blind. We didn't know who had the condition in our society for weeks. And in addition, we had initially rules. Our elite hospitals around the nation can develop these tests on their own. But because we didn't want every hospital making up its own testing protocol, we said we're going to centralize that. And the result was we lost precious weeks. Hospitals like Yale New Haven or Mass General Hospital or San Francisco General or Seattle Children's, all of them can have the technology to invent and deploy these tests, but they were prohibited from doing so that we could centralize it. And there was a lot of political conversation about this. That was ultimately just relaxed. And finally, oftentimes we do half measures because we really don't want to go whole hog on our testing. Or as we'll discuss shortly with respect to school closures or travel bans or other kinds of serious responses our society needs to make. We know what we should do, we want to do the right thing, but it's not easy, and so we kind of decide to do something half-baked. That's unwise, because we get neither the benefits of the intervention nor avoid the costs. In our case, the president signaled early on that he didn't want to hear bad news or see the government saying anything bad. And therefore, a lot of the people below him who are not scientists adopted his policy position. For example, one of the first things was, this is great, we can use this as an excuse to keep out immigrants. So now we have a legitimate excuse to shut our borders, which is, it's kind of mixing up political objectives. One is dealing with the epidemic, another is whatever our immigration policy should be. And as I said, there was a problem with the CDC test, but the more serious problem was the bottleneck that we created, the centralization, rather than the inaccuracy of the initial test, which in any case was quickly corrected. Now, as I said, testing is crucial for estimating the mortality rate and managing the outbreak for two different functions. The Chinese have tested hundreds of thousands of people. The Koreans, within days, set up drive-through testing places. All around Korea, you could just drive up and be tested. And you would walk up to one of these little cubicles, you'd sit in your car, someone would test you, and the results would be obtained. So, and WHO sent working kits to over 50 countries to test people. The United States is unbelievably far behind. I think the Koreans have tested 300 people per million, and we have tested, I think, less than 1 person per million in our society. What is that? 1 person per million is tiny. That's like there's 300 million Americans. Like we've tested 300 Americans or something like that. I mean, it's really embarrassingly small, the number of people that we have so far tested. That number is, I don't know exactly what that number is right now. Now, the overall mortality rate of the condition is probably between 0.5% and 1.5%. Scientists are still struggling right now to figure this out. This is something known as the case fatality rate, or the number of deaths divided by the number of cases. And there are many methodological and clinical things that interfere with our ability to really estimate this parameter, in addition to the problem with testing. First of all, there can be a delay between infection and death. So and if that's the case, that means the case fatality rate will be underestimated. So right now, let's say we've ascertained that there are 1,000 people that were diagnosed with the condition by testing yesterday, and we look at the deaths today, and we're like, oh, the disease is benign, nobody's dying. That's just because we looked at the disease today. If we wait longer, like 2 or 3 weeks, all of the 1,000 might have died. So when you do the computation at the beginning of an epidemic, can affect your estimate of the number of deaths and the number of cases. And so you might underestimate it. Conversely, you might be missing many mild or asymptomatic cases. Like I said earlier, there might be many people that are infected and we don't detect them. And so we think, oh, the disease is really deadly because we only count the sick people and miss all the well people. And in that case, we could be overestimating the case fatality rate. Our best estimate is that the case fatality rate is probably not more than 1%. Somewhere between 0.4 and 2.9% might be the range. And just for reference, the case fatality rate, oh, and here's some comparison diseases. The regular flu that our society deals with is about 0.1%. So about 1 out of 1,000 people that are infected by the flu die, and probably for coronavirus it'll be maybe 5 or 10 times or 15 times worse than that. Okay, now that's an order of magnitude, that's a lot worse. But it's not like, you know, SARS or Ebola, for example, which kills like 40 to 70% of the people that it infects. And here are some other diseases, similar diseases. Seasonal flu is about 0.1%. H1N1, which is a pandemic disease, a pandemic influenza that my lab studied about 10 years ago, and I'll tell you more about that. You guys were all in middle school when this disease struck, is less deadly than the flu, about 0.05%. SARS is more deadly. The previous SARS epidemic we had 10 years ago is 10% of the people who got it died. That was a much more serious disease than the current SARS outbreak. And the 1918 pandemic that swept the world contributed to a worldwide depression and killed between 30 and 60 million human beings 100 years ago, had a death rate of between 4 and 5%. When coronavirus first struck and the world became aware of it in January, people were worried that this disease would be as deadly as the disease from 100 years ago. And a further issue is that the pathogen may mutate, just like in the movie, to become better or worse. Now, usually pathogens become milder as they spread through the human population. Because if they're too bad, they kill you too easily, they kill their host less commonly. So if the pathogen is one that is a killer, it kills you before you can transmit it to someone else. So a milder pathogen has more of a chance of propagating. And that's why, as we collectively, as our species fights this germ, some of us give up our lives in order to defeat this germ. So only the milder versions spread, and then if you're, let's say, infected with a milder version, you develop immunity to the condition such that if you're then infected with a more deadly version, you might not die or even become sick from the condition. Now, the mortality is going to depend on many factors, including how many cases are detected, which is again why testing is so important, how vulnerable the population is, like the disease spreading through urban slums where people are malnourished and impoverished will have a different fatality rate than spreading through a nourished population. So how vulnerable the population is matters. How long the epidemic has been going on. So we're seeing, as additional populations are stricken with the condition, we're seeing a decline in the fatality. And on how good the healthcare system is and how able it is to actually provide care and not be overwhelmed. And this is something that I and many others are very concerned with right now, and I'll come to this in just a moment. We may have so many cases so fast and lose so many healthcare workers to the condition as well that we may be literally unable to care for the people who are sick. We may not have enough respirators, we may not have enough doctors. And this is one of the reasons that many community-level interventions need to be deployed in our society and have been deployed in other countries like China and Japan, and I'll come back to that. And ironically, as I mentioned, generally speaking, the less deadly a disease is, the more pandemic it's prone to be. But that's not always the case. So this disease is more deadly than H1N1, but more pandemic than it. On the other hand, it's less deadly than SARS, and more pandemic than SARS as well. Now, one piece of good news for you guys is that younger people appear to be relatively spared. This has been repeatedly studied in multiple samples around the world already. So I think I forgot what sample this is estimated over. So your age range, like 2 out of 1,000 people died. That's still awful. Like if 2 out of 1,000 Yaleys died, that means we would have like 10 dead Yaleys in 6 months. That would be horrible. In Korea, one Korean study of 5,000 Koreans found that 0% of the people in your age range died. But it affects, as you go up the age span, here's my age group, that's like 1 out of 100 people died. That's, getting my attention. And up until the 80 plus, about 15% died. Now, there's a lot of conversation in the media about how, well, isn't this great that only the elderly are dying? Well, yes. I mean, I would rather the elderly die than the young die. But the elderly are our neighbors and our citizens too. They're your grandparents, your parents. It's not like we should be happy that, maybe you're happy, I don't know. It's not like we should be happy that elderly people are being killed by this condition. And my best estimate is that, well, I'll come to this, but I think that in the best case scenario, we're going to have 1 million Americans infected, and at least 35,000 extra deaths in our society from this condition. That's the best case. And the worst case is far worse, and we'll come to that. So if you think about it, it's like we've added a leading killer in our society. If I had told you, you know, all the conversations we've been having in this course, if I had told you all the effort we made to stop motor vehicle deaths, you know, motor vehicle accidents are a leading killer, top 10 killer in our society, and we struggled so hard to stop those deaths. We have laws and police and seatbelts and advertising campaigns, and we're so sad when people die from car accidents. If I told you that we could miraculously hit a switch and stop those deaths, we would think that was an extraordinary triumph. Well, now we've done the opposite. We've added a killer that's just as bad as motor vehicle accidents onto all the other killers that are present in our society. At a minimum, I think. So that is a rather sobering thought. And in my view, that's the best outcome we could get. Actually, the outcomes could be far worse than that. We could have hundreds of thousands of Americans die of this condition. Some people estimate, the best estimates we have now, and they're very wide still, are that between 20% and 60% of Americans will be infected. Let's say 20% are infected. That's 60 million Americans. And let's say 1% of them die. That's 600,000 Americans die. Or 0.5% of them die. That's 300,000 Americans die. That's a top 1 or 2 killer this year in our society. Okay? So it's a serious, serious condition that we are dealing with, even if it tends to spare people in your age range. Now, I started making these slides a week ago to give you this lecture, and I've been scrambling to put it together, and I made this slide like 3 days ago. And all these numbers have changed and gone up, literally in the last few days, and I was scrambling today in the midst of all my other obligations trying to update, and finally I said, screw it, I'm not going to update these numbers. They're all bigger than they were just 3 days ago. And you can go to a website on WHO, I thought I had the URL here, but I don't, that updates these figures every day as to what the status is. China has only gone from like 80,000 to, I think, 88,000 in the last 2 or 3 days. The epidemic in China has grown a bit less. I think 84,000 is flattening. Korea has gone up. Italy has gone up. Iran has gone up. I love this Diamond Princess. It's like a plague ship. You know, it's like it's on the league tables of nations now that, you know, this is epidemic. But actually, the Diamond Princess is one of the best sources of information we have because it was all contained. Nobody came in, nobody came out, and we could just like a petri dish study. Like, okay, 700 of you on the ship. How many of you died? Ah, thank you. And that's the death rate, you know, from the condition. So the Diamond Princess has been, you know, there's going to be papers written about the Diamond Princess for the next 10 years by scientists. And here's Japan. The USA had 62 cases as of then. It's, I think, tripled since then in the last 3 days. We're up to about 108. And this is the problem with epidemics and with our leaders and you guys. And I'll come to this in a moment. You look around and you think, well, all this alarmism, why is everyone so concerned about this condition? I don't know anyone that has coronavirus. We haven't seen that many news reports about coronavirus. There's nothing much happening. Well, that's what epidemics do. Nothing is happening, nothing is happening, nothing is happening, nothing is happening, till suddenly the shit hits the fan. I mean, a lot is happening all of a sudden, okay? So that's what happens with exponential growth, and that's part of the reason it's so difficult to appreciate the reality of the situation. There is an astonishing worldwide effort of geneticists, microbial geneticists, who are working together, it actually blows my mind, who are genotyping in real time samples of this virus from around the world and uploading the data onto a shared database. This is the, I can't believe I didn't put the URL here for this one. I forgot what this URL is. You can find it. Anyway, this is the genetic epidemiology for every single pathogen that's so far been typed. As every new ones are typed, we can create the whole family tree going all the way back to the first case that we estimate is December 17, right here in Wuhan in the middle of December. And we can see, like, you know, the genotype of this branch here came from one case, probably that flew in mid-January from China to Seattle. We don't know who that person is. They infected some other people who then spread it in Seattle. We can tell. In Italy, we can use genetic techniques to identify that there were 2 people who started the epidemic in Italy. Just 2 people. And I don't know whether they were Chinese that moved to Italy or Italians that came back to China or exactly who they were, but 2 people started the epidemic there. And this same genetic technology is the basis for the rapid tests that we're using to detect the disease in other people. Now, the speed with which the epidemic grows depends a lot on the social mixing. That is to say, if you infected a group of hermits, you infected one person and a group of people who had no connection with anyone else, it might take forever for the disease to get to the second person. So your intuition about the doubling time of a disease, you should have the intuition that it depends on the nature of the interactions between the people. Initially, given the density of the population in China, and maybe given the way the disease happened to strike during an annual the Harvest Moon Festival in China, when there's a huge migration and people go back to visit their families, so a lot of people were together in public transportation and interaction, maybe even higher than usual. The doubling time in China initially was estimated at 1.5 days. Every day and a half, let's say every 2 days, the number of cases was doubling. Right now, the best estimate of the doubling time worldwide is between 6 and 7 days for populations that are mixing in a normal way. Okay? So like typical, let's say, human beings living together in, let's say, a typical way, how long does it take for the cases to double? Well, if you look at this here, if you look at the case doubling, this is exponential growth that you all studied in high school calculus. So nothing is happening for months. You know, you're going here, no cases here. It takes this long to go from 1 case to 1,000 cases. It takes 2.5 months. And then it takes another month to go from 1,000 to 10,000 cases, and then you're off to the races. Okay? And so this is what we're looking at right now. In the United States, we're like right over here. So we're thinking, oh, 180 cases. You know, that's not the way to think about the predicament that we are in. So what are the transmission modes for the condition? How does it spread from person to person? A number of ways. One way is by droplets. So like I sneeze or I cough, and little droplets come out of my body and they float through the air and they get onto your body, and then that's how it spreads. But the droplets actually fall to the ground if they're too big, so the droplet would have to literally like cough on you. You know, like really like sneeze right onto you for the droplet to leave my body and get onto your body. But if it's smaller, it could be airborne. So the virus can spread through the air. Little tiny droplets can spread through the air and go from one person to another. Another one, just like it was shown in the movie, are what's called fomites. These are surfaces. So typically these are non-porous surfaces. So it's not that you're going to get the disease from sitting on a couch, which is a ruffled surface, or even handling paper money. It's touching doorknobs, elevator buttons, your phones, smooth surfaces where the virus can just stay there. Now it's not clear how long the virus will stay there. So at least a few hours, maybe a few days. We don't yet know fully, or at least I don't know. Maybe some other people already know the answer to this. I'm sure there's someone doing investigations. We're not quite sure if there are other routes. We don't know if it's in urine or in semen or in other types of body fluids. And there's some hint that there could be fecal-oral transmission. There's increasing reports that it can spread through fecal contamination or through open sewers. And if that's the case, in places like India are going to be devastated by this condition. As the people shed the virus through their feces, it enters open sewage streams, and then it floats through the air from that stream and affects other people. There was an outbreak in Hong Kong with the last SARS virus in a building that had poor sewage that has strongly suggested that this is a mechanism of transmission that can actually take place. But more important even than the specific mechanism of transmission are the social dynamics of transmission, whatever the mode. So this is something we're going to discuss at length when you come back from vacation. We're going to talk about networks. So this is a little illustration of a little tiny fraction of a network. So this person here interacts with these two people. He doesn't infect everyone. He just infects this guy, who interacts with these two people, and he infects this guy. But this guy has a super spreading effect. This is what happened in Italy. One person infected 43 or 47, I don't remember the number.
47.
47 other people from one case. And then you're really off to the races when you have that many subsidiary vectors. Now you can use these types of transmission numbers to compute something known as the R0, the R0, which is the average number of secondary cases generated by the first case in a susceptible population. So if you had a whole network and you mapped it out, and you said, okay, given this first case, how many other people ultimately were infected? So the R naught here might be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, for example. This one guy resulted in 14 other people being infected. But there's another parameter which you can estimate, which is the RE, which I'm blocking right now what that stands for. I know the answer to this. The effective reproductive number, which is the average number of cases generated by any case in an ongoing outbreak. So on average, how many secondary cases are created by any given case? The R naught for COVID seems to be between 2 and 4. Okay? And you can compare this to other conditions like Ebola is 2, HIV is 4, SARS is 4, mumps is very contagious is 10, and measles is super contagious, which is why we have all, it's like I think the most contagious disease known, if I remember correctly. And that's why we have these awful measles outbreaks in unvaccinated populations in California and other parts of the world. So the R naught, or some measure of transmissibility, is about 2 to 4 in this case, which is for the initial case, how many subsidiary cases occur. Now, by definition, the R naught cannot be modified through vaccination campaigns, since it is defined as the number of people infected by the same person in a susceptible population. If I took you with a disease and put you in a room full of people who are immune, and I said, oh look, there's no other cases, that's not a fair test of the transmissibility of the condition. So it's a measure of the transmission in a population that can actually get the condition. So R naught is not a biological constant, it's not an intrinsic feature of the pathogen, since it's also affected by other factors, such as environmental conditions or the social behavior of the infected population. And here is how the effective reproduction number, why it's difficult to estimate that in early days, because the cases can lag given the existence of an incubation period. So imagine that you have a first individual that's infected right here, and initially they're not symptomatic. And this would be the incubation period, the time between when you're infected and when you show symptoms, okay? Which could be 4 or 5 days, let's say, in this coronavirus epidemic. Then you're symptomatic for some period of time until you recover, all right? We saw a median of 12 days in hospitalized patients I showed you a few slides ago. So it's not like the disease lasts months, you get infected, 2 to 7 days later maybe you show symptoms, and then you have symptoms for 7 to 14 days, and then you recover or get seriously sick. Now that's different than this issue of what's known as the latent period, which is when can you transmit the virus to others or not, okay? So here you're not infectious, and then you become infectious. And this is the most dangerous period right here, okay? The period of time in which you're not symptomatic, but which you might be infectious. This point doesn't necessarily need to align with that point in any given condition. Which is worse? For this point to occur before this, for this point to occur before this point, or for this point to occur after this point? Which is worse? Before, right? Because you can have no symptoms and you're spreading the disease, okay? And this is a quantity known as the serial interval, which is the time period between the first person becoming infected and the next person becoming infected. So he's not symptomatic, he's not infectious, he becomes infectious, and some amount of time later, while he's symptomatic, he transmits the infection to the next person, and that's the difference in time between those two is known as the serial interval. And that also plays a role, as you can intuit, in how rapidly the epidemic can be transmitted. We do not think, there's a lot of conversation in the literature right now is, can you be reinfected with the disease? So there are people who were tested for COVID, they're admitted to the hospital, they're treated, they get better, they're discharged, and then they come back a few days later and they're positive again. People say, oh my goodness, they got reinfected. That would be bad news if that could happen. It would mean that our immunity to the condition is not strong or sustainable. But we don't think that's what's going on. What we think is happening is bad testing. That is to say, the tests are falsely negative at the end, and the person still had the virus. We think the immunity lasts a few months for sure, and probably a couple of years. This is good news. Once you get the condition and survive, you're not going to get it again, and you won't get it for a long time, hopefully. That's good. Now, this is the most, not the most important, it's one of the more important slides I'm going to show you. This is taken from this paper here. We can imagine now plotting the severity of the condition, how deadly is it, from not too deadly at all, common cold, to very deadly, like Ebola, or here these are only influenza strains. So it's not common cold here, it's already more serious than common cold, and this is not Ebola, this is Spanish flu, which had a 4 to 5% mortality rate, okay? Versus the transmissibility, like the effective reproductive number, some like R0, some measure like that. So you can plot these like this. So this is mild, it's not very severe, it doesn't kill you, and it's not very transmissible. That's great. This is Spanish flu. Not good. Bad and transmissible. And here's the 1957 outbreak of flu, so your grandparents will remember these last outbreaks. And here's some other outbreaks that occurred during your lifetime. We've had other pandemics before, while you guys have been around. But the problem is that this one seems to be right there. It looks like it's going to be a once every 50-year kind of severity thing that you happen to be experiencing at this moment in your lives. And we hope, very much we hope, that it's not like this. Okay? But we don't know yet. We don't have precise estimates of this. This we have, I think, pretty good estimates. It's going to be much less deadly than this. But the transmissibility, we also don't have perfect estimates yet. Okay? So this is what I think we're facing. It's something that human beings have seen before. We've coped with it before. This is not Armageddon. But, it's not a trivial situation. Now, what should we do about it? How can we mitigate or confront this pandemic? Well, first of all, we can imagine that there are pharmaceutical interventions, like drugs. It turns out that, as a rule, antiviral drugs are difficult to invent and not as effective as antibacterial drugs. Okay? So drugs that kill bacteria, we have many classes of them and they work. Drugs that kill viruses, we don't have so many classes of them and they don't work so well. Plus they're more toxic. So, we will have some drugs and people are trying drugs. We're going to have drugs that help, but it's not like we're going to have some kind of drug. We can't stop the common cold. Believe me, if there were a drug that would treat the common cold, people would make billions for that drug. We would all happily pay money to avoid the common cold, but there is no such drug. We just treat our symptoms. We don't treat the disease when we have a cold. So what we're going to have to rely on is something known as non-pharmaceutical interventions, NPIs. And there are two kinds. They're what we can do as a community and what we can do as individuals. So as a community, you can have travel restrictions, like let's stop international flights, for example, or let's stop domestic flights. The president could wake up tomorrow and order the entire United States air fleet grounded, and nobody would fly anywhere in this country. And if we were facing a deadly pandemic, that might not be a crazy thing to do. We could have school closures. I'll come to that in a moment. That's an issue that's going to affect you guys. People at Yale are going to have to think about, should we close Yale? Should we close the campus or not? When should we close the campus? How do we know it's the right decision? There are a lot of adverse consequences for closing the campus. We can have rapid treatment. We can put into place procedures so that when you find a case, we detect it and treat it rapidly, interrupting the downstream cases that could occur. We can spend money and build infrastructure to do that. We can have a rapid case isolation as a policy. We can increase the ventilation by opening doors, windows, to increase ventilation, or we can have cleaning. I think I read somewhere that in Italy, they have cleaning crews cleaning the subways 3 times a day now, like scrubbing them down, top to bottom. Or personal things you can implement, non-pharmaceuticals, hand hygiene. Everyone's talking about this, and truly it's exactly what you should be doing. You should be washing your hands several times a day. Front and back, between the fingers, like really, don't just like put your hands under water and feel good. Just take this seriously, wash your hands. Self-isolation, so that means stay away from other people. There's a video that went viral, which I love, but my wife thinks is ridiculous, which is, there's this guy gets out of a bus in China and he's wearing a mask, and he's meeting a delegation, and they go to shake hands, and he goes, and then they do this thing where they tap their feet to each other as a handshaking. I've started doing that now in my lab, and people are laughing, but I think it's great, actually. My wife thinks it's nuts, but I think it's sort of. Anyway, so don't touch each other, don't hug each other. It's very difficult. You meet someone, you're like, nice to meet you, or hug you, or if you're Greek, you kiss on both cheeks. Not good. Masks is very difficult to know whether masks help. It's quite clear that you're wearing a mask reduces whether you transmit the disease to others, so that's great. Does the mask prevent you from getting the disease? It probably prevents the types of transmission that involve droplets, Like I cough on you and it would go right into your nose, it's kind of gross. The mask will stop that, but little airborne particles can go around the mask, so I don't know if it'll stop that. Unless you have like a respirator, like a gas mask, which, you know, like a guy in Contagion that was selling the Forsythia was walking around in, that would, you know, help. And then respiratory etiquette, you know, don't cough on each other and stuff like that. So, so there are a variety of personal, community, and environmental non-pharmaceutical interventions, and general principles are that they should be initiated early in a pandemic before local epidemics begin to grow exponentially. So you should all be isolating from each other. You should all be implementing these things right now. There's no reason to wait to do them. They should be targeted toward the nexus of transmission, that is to say in affected areas where the new virus is circulating. Seattle should have already been doing that. They should be layered together to reduce community transmission to the greatest extent possible, so you should be using more than one at a time. I want to highlight a difference between something known as, what everyone is using the word quarantine, and there's another term of art in public health, which is cordon sanitaire. There's a difference between the two. In a quarantine, you quarantine sick people. In a cordon sanitaire, you isolate everybody, whether sick or well. You create a clean ribbon, a clean boundary around the city, for example. You say no one can come in or out of the city, whether they are sick or ill in the city, or sick or ill outside the city. And that's the technique that's being used technically, but we're all calling it a quarantine. There's more evidence that shutting down schools helps, and I'm going to come back to that. Actually, shutting down schools is much more effective than shutting down subways or air travel. And hand washing, as I said, really helps. Now why? Why are we doing this? The reason we're doing this is to do something known as flattening the epidemic. So imagine here that this is the daily number of cases, and this is the number of days since the first case. You should have the sense that the epidemic is going to rise to a peak, and then gradually begin to fall as it runs out of other people to infect. Okay? And what we want to do is we want to implement a series of procedures which converts this bell-shaped curve into this one, flattening it and postponing it. Even if you have the same total number of cases, even if the area under the curve, if you were to integrate it, is the same, so ultimately you have the same total number of people affected by the condition, it's much better to have this. Why? Well, first of all, you don't overwhelm your healthcare system. We're going to have a problem in our country because when people start getting sick, there are going to be too many sick people for the number of beds in the cities. So we don't want to have a point where we're spiking with thousands of people sick at the same time. It's fine to have 1,000 sick people, but we only want 10 sick at a time, or 20 sick at a time. Discharge them and admit new people. So flattening the epidemic is really useful for unburdening our healthcare system. So doing all the non-pharmaceutical interventions that I'm discussing right now is essential as a society. And this also should change. So there's another crazy kind of ideology right now, which is that if I don't shake your hands, I'm like less of a man or a woman, I don't know, less of a strong person, let's say, and or I'm not showing proper altruism. I should be brave and shake your hand and take the risk of getting the disease. But that's the wrong way to think about it. Actually, the right thing to do for the good of our society is not to shake hands. To really show altruistic commitment to the well-being of our society, you need to narrate. Altruism is not about I'm taking a risk by touching you. Altruism is I am contributing to our society by not touching you. Okay? That's the commitment that we need to make right now. To bring this down so that we postpone the cases and our doctors and our health and nurses and our healthcare system can work. Now there's a further subtle advantage of this. If we can postpone the number of cases till past some time right here, more of the cases will occur at a time at which we humans will know better how to treat them and maybe even have invented a vaccine. So if you push the cases out into the future, you find yourself in a circumstance in which we've invented a vaccine so you can prevent additional cases. All right? So that's a further advantage of pushing it. So we want to flatten and postpone the epidemic. Right now, the estimates are that 20 to 60% of the US population will be infected, and the fatality rate is still unclear, although I have alluded to it for a little bit already. Now, one of the reasons this healthcare thing is important, we have some hints of the importance of this from Chinese data already. This is a nice little study published by a group of Chinese investigators that was just published like a couple of weeks ago in Lancet Global Health. They looked across districts in China at the cases per thousand and at the mortality rate. And they found that the more cases per thousand that any district had, the higher the mortality rate. So the healthcare system is overwhelmed. Too many people are sick per person right now, and so more of them are dying because we can't care for them. Do you understand? So this type of a line is exactly what we're trying to avoid. We're trying to flatten the epidemic, to push the cases out, and decompress our healthcare system. Well, what about travel restrictions to flatten the epidemic? This panel A here shows the estimated delay in the peak of the epidemic. What happened? What? Oh, sorry, Ben.
I just had a quick question. What do you think, like, if the Chinese epidemic is truly flattening out, and they've stopped, like, well below 20% of the population getting infected, like, what has
all the Chinese have done, this is another, the way I describe this is my new line. So think about the force the Chinese are applying. They have put 700 million people under house arrest for 2 months. Basically 700 million people, and this is, I have Chinese friends who reportedly tell me, yes, we're going stir crazy, their food is delivered, there are a lot of funny humor, gallows humor in China right now. 700 million people are stuck in their homes for 2 months. So, and you have a government that can do that. So you have an authoritarian government and a culture that is willing to do that, right? That is kind of a collectivist, long-term, thousands of years of notion of suppression of individual needs for the benefit of the collective, okay? So you have all the circumstances which make it. That is an incredible power that's been deployed by human beings to do what? Stop something that must be equally powerful. So this should give you a sense of how powerful the thing we are fighting is if the techniques we have to use are this technique of putting 700 million people in lockdown, okay? That should sober you up. So what the Chinese have done is they've not eradicated the condition, they've stopped the spread. Once they start removing their people from quarantine, the disease will emerge. But what they've done is they've flattened the epidemic. Right? So I think what they're going to do is start releasing their cities from quarantine sequentially in a very rational way so they can cope with sickness and slowly manage what's happening. So they have not, eliminated the condition. Do you understand what they've done? They brought it down to like 50 cases per day in the country, which is unbelievable. So, I am very impressed, but I have many concerns about the Chinese political system, but I'm very impressed with what they've done in terms of handling the epidemic. They did some things really bad at the beginning. So the doctor in Wuhan, the young doctor, he shared with his medical colleagues that he had seen a very unusual case of pneumonia using some kind of social media app. And he was, there's a crime in China, I think, called rumor mongering. And he was hauled in by the authorities and accused of rumor mongering, and they had to get rid of all the chats, but he was right. We don't have that in our society, thank God. We have other issues, but that's not a problem. So anyway, this is Chinese data. Okay, any other questions? So I'm speaking a very professorial clip. What time is it?
3:30.
Oh my God. My lecture is twice as long as it needs to be. Oh my God. Oh my God. So let me just show you very quickly about some others. So these are travel restrictions. This is because I've never given this lecture before, so I haven't paced myself at all. So I'm only halfway through, so I'm going to talk very fast now. This looks at various types of, given 4 different conditions, the United States and Great Britain with a high transmissibility condition and a low transmissibility condition. If we stop 90% of the flights coming to the United States 30 days after the onset of the epidemic, we'd only postpone the epidemic by 10 days. If we stop 99% of the flights coming, we postpone the epidemic by 28 days. If we stop 99.9% of all incoming flights into our country, we only postpone the epidemic by 42 days. So stopping international flights is not going to stop the epidemic. You can gain some time, but not a lot. On the right shows a model of estimates. This is from a paper in Nature from a long time ago. We know all about this. What happens if you close the border and implement, so BC is border closings, border controls, AC is all American airports are closed to internal traffic. So if we close our borders and stop all flights in the United States, the peak would be delayed 42 days. So these types of interventions would be very dramatic and wouldn't necessarily buy us that much time. School closings are very effective, amazingly. So the school closings, there's a lot of information on this slide. I'm just going to focus on the median transmissibility. So it's not highly transmissible, it's moderately transmissible, and two different things I'm going to describe in the top and in the bottom. And in the bottom, what we find here in the blue is that for 3 different household policies, the blue one up here shows voluntary quarantine of households identified with a clinical case for 14 days. So what happens if they have a case, they stay home for 14 days, the cumulative attack rate, that will decrease it by 24%. Very easy thing to do. If you're sick, stay home, okay, for 2 weeks at least. Peak daily attack rate goes down by 1%, and the delay in the peak is a 4-day delay in flattening the epidemic. This here looks at school closures. What happens when we have reactive school closures? That is, we close 100% of the schools, when the first case strikes a school, it results in 24% reduction in cumulative attack rate and these other benefits here. So school closures are very effective. In part also because when it's for small kids, even if they are not sick themselves, it keeps the parents at home and keeps the kids from being the little vectors that they are. Well, how have these things worked in the past? We can look at the 1918 pandemic. This was a wonderful study that collected data from 43 cities in the United States, and it looked at a variety of non-pharmaceutical interventions: isolation or quarantine, school closures, public gathering bans, isolating and quarantine and school closures, or various combinations of these things. So what fraction of cities had implemented these things for more than a week, and what was the median duration of these non-pharmaceutical interventions? And then having done that, what these investigators did is they looked at, did they work or not for the flu pandemic. So this shows here on the y-axis the public health response time. The public health response time is the time in days, either positive or negative, between the date at which the weekly excess death ratio, that is to say the excess deaths, first exceeds twice the baseline for influenza. So usually 1% of people die of influenza. What is the date during the time of the epidemic that 2% of people are dying per day of influenza, or whatever it is? On that date, that's the date we're going to mark in this city, and we're going to ask, in relationship to that date, did the local authorities implement the non-pharmaceutical intervention before that date, before the excess deaths had doubled compared to the usual rate, or after that date? Okay? So here, the authorities are implementing school closures in advance of this double death rate, and here afterwards. And then here we can go back and look a century later, how many excess deaths occurred? And the bottom line is, the later they implemented the school closures, the more deaths that occurred. The earlier you are in implementing school closures, the more lives you can save. And this also looks at the number of days, how long were they implemented, and it finds a similar result. This slide shows 2 different cities. It looks at school closures and public gathering bans. Here's what St. Louis did. St. Louis, so here shows the first pneumonia case occurs here. Here, at this little clear dot right here is when the death rate had surpassed this 2 times threshold. And you can see they implemented the school closures before that point and for a long time, and the total number of deaths was 358 per 100,000 population, compared to Pittsburgh, where they had almost 3 times as many deaths because they implemented the school closure too late and for not long enough in that situation. I was going to tell you about some work that we did looking at something known as dueling contagions, but I'm going to skip that. And I'm going to tell you now about some very active work in my laboratory right now on forecasting the epidemic. So how can we predict what's going to happen? One thing we can do is use testing and modeling. Another thing you may have heard about is online searching. So we can use search data. People, if Yale is all of a sudden are searching for the flu or sniffles or how do I treat a fever, that could be a signal that you guys are sick. Or we can use population movements with phone data, which I'm about to show you, or a new idea involving network sensors, which I'm just not going to have the time to show you, but it's crucial because with the Yale undergraduates, we are developing an app that I'm going to ask you guys to help us debug over break, so that when Yaleys return from break, we're going to have an app that's being used by Yaleys, Yale students, to monitor the epidemic, the risk of the whole college, and their own personal risk. And I'll show you about that in just a moment. In collaboration with Chinese colleagues, we've done a project where we had phone data that had 18 million transits of people through Wuhan from January 1st to January 24th. So we were able to track everybody that transited through Wuhan, or in Wuhan and left, or this is a central transportation hub, Wuhan is in China, or came through Wuhan and spent at least 2 hours there, and then spread out around 300 prefectures in China. And what we were able to show is that the outflow from Wuhan, which is shown in this colored thing, tracked the number of diagnosed cases. Without even knowing who was sick, we could use mobility data based on phone records to predict who was going to get sick, where the epidemics were going to strike, and how severe they were going to be throughout China. This shows transits through Wuhan to these other destination prefectures, and this is when the quarantine comes crashing down. You can just see the Chinese stopped moving on the 25th, and there were only 3,000 people left in the whole prefecture after that date, probably local authorities. This shows population outflow from Wuhan on a log scale on the x-axis, and confirmed cases of COVID. So this population movement from January 1st to January 24th, and confirmed cases through February 12th, we can almost perfectly predict where and how severe the epidemic will be using transit data. Now, I'm going to very quickly walk you through an idea that ordinarily I give a 1-hour lecture on, and now I'm going to spend 10 minutes on it, because it's the idea that I need your help with. If you, usually, an epidemic has an S-shaped diffusion of innovation curve. So here's time, and here's the percent of people affected. If you map a human social network, and this is a real network of 105 college students, every dot is a student, and every line represents a friendship relationship between students. Different people occupy different locations within this network. This student has 4 connections, this student has 6 connections. This student is more popular than this student. And this student has 6 connections, and so does this student, but this student is located in the middle of the network, and this student is on the periphery of the network. This, you should have watched, I hope, my TED Talk on this, so I talked all about this. You should have the intuition that this person here, in the middle of the network, should get whatever's spreading earlier in the course of the epidemic. So they're like canaries in a coal mine. If we can identify central people and monitor them, we'll know what's going to happen to the population of Yale as a whole before it strikes the population as a whole. So these 6 people might be our little sensors. They serve as advance notice of what's going to happen. And these 6 people are better than the usual approach, which is to have 6 randomly chosen people from the population. So the CDC or Yale Health might say, let's monitor what's happening with flu at Yale, and they say, let's pick 10 Yaleys at random. That's not as good as picking 10 popular Yaleys, okay? So in the TED Talk, I talk about this trick of using the friendship paradox, that your friends have more friends than you do. I don't know if you knew this. Did you know that your friends have more friends than you do? You did know that before or after you saw my talk? Before? Who knew that your friends have more friends than you do before? Oh, that's great. Did you know that just experientially because you're not so popular? Or did you notice that because you studied the mathematics of degree heterogeneous graphs? Probably you know. Anyway. Yes. Anyway. All right. So what that means is that if you plot the S-shaped diffusion curve, the curve should be shifted to the left among central individuals compared to the general population. Or the daily incidence should peak this amount of time delta t earlier in the central people than in the random people. So we did a study of 700 students. This was when I was still at Harvard. We monitored, this was 10 years ago, so we had to do it with text messaging and an Excel spreadsheet. Now we're going to do it with an app at Yale. And we predicted this would happen, and this is what we observed. Exactly what we predicted. The epidemic peaked 2 weeks earlier in the central people than in the population as a whole. So we can predict when the epidemic will strike when we start seeing it in the sensors in the network. In fact, 6 weeks before the curves diverged. So I knew 6 weeks before. That's a huge lead time in this situation. And I was going to show you a little video which I don't think I'm going to show you, of the epidemic spreading. I'll just give you a hint of it. This shows 700 students, and the dots are going to start lighting up where the epidemic is. Not much happens initially, and then you're just blooming. This is the epidemic of flu taking root in the student population. And I discussed this. This is, I tweeted this video out earlier today, and it's also available with the manuscript. So it's saturating, the epidemic. Now what we've done here at Yale, and I'm going to release to you soon, I'm going to email this class, is we've developed a little app, and I'm hoping very much you will sign up for this app. We call it FluSite. You don't have to sign up for it, but what we'll do is we'll email you a link, and it should be Android enabled as well. You will sign up for it. You'll tell us a little bit about yourself. We need your phone number to authenticate it. Once you sign up, we'll take your phone number. We're not going to call you. We just use your number as a unique ID. And we're going to ask you to nominate your friends, like who do you hang out with face to face, who are your friends. 0 people, you don't have any friends, or 1 person, or 10, or however many friends you have, it doesn't matter. You don't have to fill the list. And then we're going to ping those friends and see if they want to join. They don't have to join. And then we're going to see what college you're in, and your sex, and your gender, and a few other trivial things. And then we're going to collect some survey data about, have you had in the last 24 hours the flu or not? And if you say no, that's the end. You don't have to answer any more questions. If you say yes, you have to tick all the boxes, and tell us if you saw a doctor, and tell us if you self-isolated. So it's like a 1-minute little survey. Once a day, at random, between noon and 9 o'clock, you'll be pinged, and you'll be asked. You don't have to respond right away. Anytime in the next 24 hours, you can respond. And every day, you're going to get pinged and asked, if you have any of these flu symptoms, no, you're done. If you do, which ones do you have? And then as soon as you answer, you'll be told what is the current risk at Yale of flu, and what's your risk, okay, in relationship to what's happening in the population. So Yale's risk might be high, but you're hunkered down in your room and you've not talked to anybody and you have a very low risk. Or Yale's risk might be low, but you might be working in a biosafety level 4 laboratory or something, okay? Actually, that's not how we're tracking it, but you get the idea, all right? So we're going to release this app. We're going to test it with my students and a few other people, the global health students and some others, over break. And then we have a debug. I want you to mail me any bugs that you find in it, email me. So by the time it comes out, it's going to be broadcast as available to all Yale students, and the administration has approved this, and everyone's very excited about the use of this. I hope very much that many students sign up, which makes the tool better, and we can build machine learning into it so that we can better predict what's going to happen. That won't be perfect at the beginning, but it'll get better as time goes by. And then maybe roll it out to some other colleges, and if we're really lucky, build a tool that can actually be used at a metropolitan scale around the nation. Because what the tool also does is it gives you advice about whether to self-isolate. So if you are at very high risk, it says you're at very high risk, maybe you want to lower your social connections, your contacts, not ditch your friends, but don't interact with them so much, okay? Or use Skype or some other means. Do you understand? All right, so I'd like to close with just some reasons for hope and caution. I think it's likely that the case mortality rate that's being bandied about is not as high as people are saying. I think it's probably going to be about 0.5%, which is still high. I think the basic reproductive number may not be as high. I think that number is going to probably come down too. I think mitigation, even short of China scale efforts, will help. And I just hope our country doesn't do them too late. If you're going to close schools in your district, why wait until the first case? Just close them now and save some lives. The seasonality effects may be strong for the condition, which means that as the warm weather comes back, it may be the case that we get spared in the northern hemisphere, but all that means is the disease is just going to go to Africa and India, where it's going to decimate the populations and then stay there until next winter, when it'll come back and affect us again. Drugs might help to some extent in individuals. I don't think the ribavirin class is going to help, but maybe. And the vaccine development, I'm not very optimistic about vaccine development. And just like in the movie, it'll take at least 18 months to develop and circulate the vaccine. And I think we're going to have to use an active virus, an attenuated virus to do this. And so it's going to take a lot of time, just like in the movie and all the problems that they described. The efforts to design a coronavirus vaccine so far have generally not been so successful, and previous use in the last SARS epidemic of ribavirin also has not been so successful. And I need to highlight that the situation in Africa and India could turn out to be quite serious and the pathogen could spread, as I said, in winter over there. Both very cold and very hot weather seem to compromise viral spread, and from Chinese investigations, what we can tell so far is that the optimal average temperature seems to be somewhere around 40 degrees for transmission of the virus. So very hot, very cold places are not as much transmission. So it's still hard to forecast what will happen. Finally, I just want to say a couple things. We don't fully understand why epidemics end. They end. Epidemics end. One reason is that anyone susceptible to disease may be killed. So there's no one susceptible anymore. Or the people that survive are immune. That happens. But there seem to be other very mysterious reasons why epidemics sort of wind down. And unfortunately, over the last 12 years, 4 new human coronaviruses have been identified, including the original SARS coronavirus and something you may have heard a couple of years ago, the Middle East Respiratory Syndrome, MERS. Some people predict, and I'm probably one of them, that the SARS-CoV-2 will simply become endemic in our species like other cold viruses, and it's just going to become part of our lives, a newcomer to the world of pathogens that we humans must confront. It's just going to be there from now on. We have to get used to it. But most of all, I just want to highlight that we're still in the early days of the pandemic, and we really can't know exactly how things are going to turn out just yet. Thank you. That's today. So, does anyone have any questions? Just a few minutes before I let you go. You want to ask? Because now's a good time. Anyone curious about any questions? Any concerns you had that I didn't address? Yes.
Why is it temperature dependent, like the spreading of disease?
We don't know fully. Part of it is the human host. So the winters are very dry, and they're very, so they're not very humid. So our mucosa are not as moist and are not as able to resist the pathogen. So part of the weather is not about what it does to the virus and what it does to us. Also in the winter we tend to be indoors in close quarters with each other. So part of it is a change in human behavior with the weather. But it may also relate to like ambient temperature and humidity and how it affects us. Other questions? Yes, Stephen? I don't think that there's any good science to support that intervention, nor do I think the epidemic warrants it just yet. But I am not convinced that our administration is very guided by science. So and if we're going to stop domestic air travel, we should do it sooner rather than later. Basically, if you're going to panic, panic early. The best not to panic, but if you are going to panic, panic early. Because otherwise you get none of the benefits. We shut down air travel after everyone's on. So I don't think you guys are going to fly home and not be able to come back in 2 weeks. That's not what I think is going to happen. Other things might happen. It's remotely possible the epidemic will explode in eastern Connecticut in the next few weeks, and Yale may tell you don't come back, stay away for longer. That could happen. So I think they send out a notice to students saying, if you have medications or other important possessions, take them with you when you go home on break. Did you get that message or not? Yeah, you got it. Yeah, that's a good advice. Other questions? Yes, what's your name?
Sarah.
Sarah.
This might be redundant, but it's like the best way we can not get infected just by maintaining good hygiene and not interacting.
Yes, people up there, if you're an introvert or you have autism spectrum disorder, this is your time to shine. You just don't interact with anyone else. This is a great moment for you, and we're all very grateful. The thing is, remember, the reason for you not to interact with other people is not so much to reduce your own risk, which is in any case small, it's to interrupt transmission chains, right? So you're doing a public service if you stay away from other people. Thank you for staying away from us. Other questions? Yes, what's her name?
Rachel.
Rachel.
Do you think Yale's going to cancel all these international programs in the next few months, especially once we focus on like study rounds?
I think what's going to happen is, if I had to predict, I think there are going to be enough outbreaks in enough places that, from a legalistic point of view, Yale's not going to want to be responsible. Like, how would they explain it to your, even if the risk was tolerably low, how would they explain it to your 500 maybe? Then you shouldn't be going anywhere. But if we're not, and we're just sort of having kind of percolating stuff, then maybe you should, but you're going to run a risk. The main risk is not so much that you'll get sick, you guys will get sick and die yourselves. The main risk is you'll be stuck in a place that is with a raging pandemic, borders being shut down. It's not a joke. Hospitals inundated, authorities very twitchy, and you'll be stranded somewhere. And it'll be difficult for you to sort yourselves out. It's not easy to be. I've been in some circumstances like that in my life. When there's, you guys take the civil order. Have any of you ever been? None of you have seen a run on a bank, but have any of you ever seen a run on a grocery store? Have you ever been in a grocery store? Maybe during a hurricane. Maybe you were in North Carolina or South Carolina, and people panic, and there's panic buying. Raise your hands if you've ever seen panic buying. You've been in a grocery store. It's weird. I mean, you're used to going to a grocery store and getting whatever you want. And you go into a grocery store, there's no food. And you suddenly realize the average American city only has food available for about 48 hours. Same with gas. And so it's tough to be in those types of circumstances if you don't know what you're doing. Yes, what's your name? Gail.
How would it turn something that was manageable? Would it, like, if it mutated in me, or you just mean that it would spread more than?
No, I mean, even though we know the mortality rate is lower, it could mutate and get more deadly. I doubt that's going to happen. But another way it could become like the Spanish flu is the reproductive number could be higher, and that we still don't know that exactly. So I think the case fatality number is going to be between 0.5% and 1.5%, both of which is below Spanish flu. But we don't exactly know the reproductive number yet. That could change, as cases get better at reporting. And so you could move up. You could move up in that 2x2 space and get to be a serious condition. Yeah. Other questions? Yes.
When do you think we'll reach like the peak of the pandemic?
I don't know. There are people who have forecast when the peak will occur. So the peak, I think the peak is forecast to occur in between 3 and 6 months from now. That also is changing, and there have been published results by very expert people. I just don't know offhand. It's not about to peak, if that's what you're asking. But this is it's seductively quiet right now. It's seductive. It's like a shark into the water. Don't panic! But no, that's the problem. If there's a disjuncture, we're not accustomed. We're accustomed to linear growth. We're not accustomed to exponential growth. It's not something you guys have a lot of experience with, or any human being has. Other questions? Okay, go have a great break, and I will see you on the backside. And please sign up for the app. When we send you an email, it would help us a lot to advance science and to help our community.